Hi, today I will be giving you guys a brief tour on systems of distinct representatives, also known as SDRs. In this presentation, I will be providing several definitions, introduce a powerful theorem, prove this theorem, and give you guys some problems to do. So here are some definitions. I will first define a set system. Let's say sets A1 all the way to AN are indexed by natural numbers from 1 to n. We will refer to them as a set system. So what is a complete SDR? Well, it is a set that consists of x1 all the way to xn, such that for all I between 1 and n, xi is an element of AI, without any of the two x's in the set being the same. Conceptually, for example, consider a scenario like this. There are n people, and each person wants to adopt a puppy, and each person has a set of puppies that they're interested in. Suppose that no one can adopt more than one puppy, and everyone must adopt a puppy from their set of interested puppies. A valid way for people to adopt puppies like this would be an SDR. I am not sure if that helped explain this. Although in this presentation I will focus on complete SDRs, I will still provide the definition for partial SDR. So a partial SDR is a set of distinct elements from x1 to xk, such that for all distinct integers j1 to jk, which are between 1 and n, xi is an element of aji. So conceptually, unlike the example that I noted in the previous slide, in this case, not every person gets a puppy. Let's consider this very simple example. Let n be 2. So A1 can be the set that consists of elements x and y, and A2 also be a set that consists of elements x and y. We can easily create a SDR by creating a set where x1 is x and x2 is y. The set A1 can be represented by x and A2 can be represented by y, and x does not equal to y. Now, consider this example. It is fairly straightforward to see that it is impossible to get an SDR. Overall, there are only two distinct representatives from the sets collectively, and they're x and y. And there is no way for you to create a set where there is a distinct representative from each of the A1, A2, and A3. So for example, if you pick x for A1 and then you have to pick y for A2, and there's no way for you to pick a distinct representative for A3. And if you pick y for A1, then you must pick x for A2, and there's still no way for you to pick a representative that is distinct for A3. However, what if A1, A2, A3, and A4 are like this? Unlike the example from the previous slide, there are 4 sets in this set system. However, there are 6 total possible representatives. Will this work? It is clear to see that it is also impossible because the first three sets themselves have no SDR for the reason outlined in the previous slide. So adding another set to it still has no SDR. To generalize what you saw on the previous slides, there is a necessary condition for a set system to have SDR. The necessary condition is that for every set of i's from I1 to ik, subset of the set of natural numbers from 1 to n, and for every k greater or equal to 1, the sides of the union of all sets A indexed by the elements of the above set is greater or equal to k. For the previous slide example, which does not have an SDR, the condition obviously does not hold, since that there is k3 for A1 to A3, and the sides of their union is only 2, which is x and y. The necessary condition is pretty trivial, I guess. Another way to represent the condition on the previous slide is called the Hall's marriage condition. In this case, the necessary condition for the possibility of marrying each of the n boys to a girl that he knows is that for each possible k of the boys, for k between 1 and n, they know at least k girls between them. This is completely logically analogous to the condition on the previous slide. Turns out the condition is not only necessary but also sufficient for the possibility of SDR. This is actually a very powerful theorem. According to Hall's theorem, a family of sets has an SDR if and only if it satisfies the Hall's condition, which is for every k greater or equal to 1 and every set I1 to ik subset of the set of natural numbers from 1 to n, the union of a's with index included in that set is greater or equal to k. This is a very powerful theorem considering how simple Hall's condition is and that it is a sufficient condition. There are many proofs of this theorem, so I will write one via induction. If you want, you can do another one as a response to my presentation. The forward direction is very trivial. Now I will prove the sufficiency condition by induction on n. Let's say the base case is 1. If A1 is non-empty, then it is trivially true, since one of its elements can just represent. Now for the induction step. Consider a set system that consists of A1, A2, all the way to AN. Suppose that the theorem is true for a collection of k sets, for k strictly less than n. Suppose sets A1 all the way to AN satisfy Hall's condition, then we must ultimately show through induction that there exists an SDR for all these sets. For the induction step, there are two disjoint cases to consider. In the first case, it is true that for every k strictly less than n, the size of the corresponding union is greater or equal to k plus 1, which is larger than the requirement for Hall's condition. I mean, this makes it easier to prove. And the second case is that it is not true. For every k strictly less than n, the size of the corresponding union is greater or equal to k plus 1. This basically means that for some k, the size of the corresponding union is exactly k. So, for case 1, to prove this, you select an arbitrary element xn from the last set of the set system, which is an. And then you define n-1 new sets, b's, where bi is defined as ai remove xn for all positive integers I strictly less than n. Now, for each k strictly less than n, there are two cases for the size of the union of all corresponding b's. When you remove xn from all the sets that are strictly in front of an, either xn is originally in some of those sets, or it is not originally in any of those sets. Either way, after xn is removed, the size of the union of the resulting sets would still be at least k, since case 1 states that the size of the unions of all corresponding set A's is greater or equal to k plus 1. So, having an element removed, it is still greater or equal to k. Now, by induction hypothesis, we can see that all the sets that are strictly in front of an have SDRs, even if you remove xn, and you would just let xn, which has been removed from all previous sets, you let that represent an. Since it is removed from all previous sets, it will be distinct from the representatives of the previous sets. Then you will have a valid SDR for a set system of A1 all the way to AN. So Hall's condition is sufficient for case 1. Now, case 2 is a little bit more complicated. Without loss of generality, suppose that the premise, case 2, is true, and for any k strictly less than n, the size of the union of the corresponding case sets is greater or equal to k. For the sake of this proof, we will assume, without loss of generality, that the size of the union of the case sets of A's is strictly equal to k, because it is much simpler to prove, and if it works for the size of the union equal to k strictly, then it can definitely also work for greater than k, since there would be even more possible representatives to work with. By the induction hypothesis, suppose Hall's theorem is true for any collection of k sets for k strictly less than n. To prove that Hall's theorem is sufficient for case 2, we need to show the following. For all integers I greater than k and less or equal to n, suppose we define bi to be the set ai, remove the union of all sets that are indexed strictly less than I. If we can show that the set of xk plus 1 all the way to xn is an SDR for the set system of bk plus 1 to bn, then we are pretty much done. Also, note that bi cannot be empty, because by our assumption, I is greater than k strictly, and since that, the size of the union that we remove is exactly k. Since n minus k is strictly less than n, we only need to show that the set system bk plus 1 all the way to bn satisfies Hall's condition. To make things easier, instead of calling them bk plus 1 to bn, I will call them bi1 to biw. So there are w sets. Note that when you are finding the size of a union of a bunch of sets, if you remove elements that are from one of those sets, and those elements are also in another set, then the removal of these elements from one of these sets would have no impact on the size of these sets' union. Therefore, the union of A1, A2 all the way to AK, union with the union of BI1 all the way to BIW, will be the same as the union of all A's from A1 to AN. Since the size of the union of A1, A2 all the way to AK is K, and the size of the union of A1, A2 all the way to AN is K plus W. Since B sets have no elements in common with other sets, since all the B sets are basically corresponding A sets that remove the union of all sets in front of them, we can infer that the size of the union of BI1 all the way to BIW must be greater than W. Hence, it satisfies Hall's condition. Since W is strictly less than n, by induction hypothesis, we know that there is a SDR for the set system of bk plus 1 all the way to bn. Since the set of x1 all the way to xk is an SDR for a1 to ak, and the set of xk plus 1 all the way to xn is an SDR for bk plus 1 all the way to bn, we can infer that the set x1 all the way to xn is an SDR for a set system a1 all the way to an, because if a set is an SDR for the set system of bk plus 1 all the way to bn, then it is an SDR for the set system of ak plus 1 all the way to an. And by the way we constructed the set system of bk plus 1 to bn, we can ensure that all the representatives are distinct when combining with the previous sets of a1 to ak. Hence, case 2 works. And since case 1 and case 2 both work, Hall's condition should be sufficient for the existence of SDR. And here are the sources, and here are several discussion questions that you guys can take a look at. Thank you.